Hello students, welcome to my channel. In this class, I am going to teach you derivation of CR equations. Let us start the topic. So, before going to derive the necessary conditions for f of z to be analytic, means derivation of a Cauchy-Riemann partial differential equation. First of all, let us define analytic function. First, analytic function, a single valued function f of z which is differentiable at any point z0 is said to be analytic at the point z0. If a function f of z is analytic at every point z belongs to domain D of f of z, then f of z is said to be analytic in the domain D. Now, the necessary condition for f of z to be analytic, that means derivation of a Cauchy-Riemann partial differential equation. If a function f of z, which is u plus iv, is differentiable at any point z, at any point z, and the derivatives ux, uy, vx and vy, that means del u by del x, del u by del y, del v by del x and del v by del y exist, then f of z satisfy the CR equations. The equations are del u by del x is equal to del v by del y, del u by del y is equal to minus del v by del x. So let us proceed to derive Cauchy-Riemann partial differential equations. Let W is equal to f of z is equal to u of xy plus iv of xy. This is equation 1. We have z is equal to x plus iy. Then delta z is equal to delta x plus I delta y. Here, given the function f of z, given the function f of z is differentiable, is differentiable at z. So we have limit delta z tends to 0, delta 8 by delta z is equal to limit delta z tends to 0 f of z plus delta z minus f of z by delta z must exist both on real and a imaginary axis. So, it is the limit delta f by delta z must exist both in real and a imaginary axis. So this implies limit delta z tends to 0 a delta f by delta z is equal to limit delta z tends to 0 u of x plus delta x, y plus delta y minus u of xy divided by delta z means delta x plus I delta y plus I b of x plus delta x y plus delta y minus b of x plus iy by delta x I delta y. So this is equation 2. So limit delta z tends to 0, delta f by delta z can be expressed as in equation 2 because the function f of z is given here, u of xy and I v of xy. When delta z tends to 0 along real axis, then delta z is equal to delta x, delta y is equal to 0. So when delta z tends to along real axis, we have delta z is equal to delta x, delta y is equal to 0. So in that case, we have f dash of z is equal to limit delta x tends to 0, u of x plus delta x, y minus u of x plus y, this is u of x plus x comma y. So this is u of x comma y by delta x plus this is plus I v of x plus delta x y minus v of x y by delta x. So which is equal to ux plus ivx. ux plus ivx. So this is equation 3 because ux and vy exist and it is given. Next, when, so this is equation 3. Next, when delta z tends to 0 along imaginary axis, then delta z is equal to delta y and delta x is equal to 0. We get f dash of j is equal to limit delta y tends to 0, u of x y plus delta y minus u of xy divided by I delta y. Then plus I v of x y plus delta y minus v of xy by I delta y. So this value will get which is equals to 1 by as uy and vy both exist. Since f dash of z exists, then equations 3 and 4 are identical. So we can write, so we have what actually we are getting? Ux plus I Vx is equal to Vy minus I Uy, from which we get Ux is equal to Vy, Vx is equal to minus Uy. This implies del u by del x is equal to del v by del y, and del v by del x is equal to minus del u by del y. So here del u by del x is equal to del v by del y, del v by del x is equal to minus del u by del I, which is the required Cauchy-Riemann equations. And these two equations are necessary conditions for a function f object to be analytic. Okay, with this the topic for today class is completed. I shall meet you in my next class with a new topic. Till then, goodbye.